I don't like the look of this differential equation. I don't think this might be a good approach. Let's have a look at a problem from one of the hardest physics competitions in the world, the International Physics Olympiad. So this is a 2016 problem from the Olympiad in Switzerland, and surprise, surprise, it is about the Large Hadron Collider. As always with Olympiad problems, we start off with quite a lot of information. And we're given the circumference of the ring, 26,659 meters. It is a huge ring underneath the city of Geneva. Number of bunches per proton being 2808. Number of protons per bunch, 1.15 times 10 to the 11. These are humongous numbers. So let's have a look at the first question on the accelerator. So assume the protons are being accelerated by voltage v such that their velocity is very close to the speed of light. Now immediately as I'm reading this, I'm probably thinking that at some point throughout this question, I'm going to take v to be approximately equal to c. We're also neglecting any energy losses due to radiation or collisions with other particles. Perfect. So we want to find an exact expression for the velocity v of the protons as a function of the accelerating voltage v. And this here is for 0.7 marks. Let's see if we can score them. Now first I'm going to show you what not to do. It's on purpose, I promise. This question is most likely going to be comparing the theory of relativity with some of the classical approximations. So classically, we can say that the energy acquired by electrons EV is going to be equal to a half mv squared, which is the kinetic energy of electrons. We've got a problem with this equation though, and that is that if we keep pumping up more and more voltage, the velocity will keep increasing more and more, and there is nothing in this equation that prevents us from exceeding the speed of light. So we're going to need a different type of relativistic equation. So we're not going to use this one. In relativity, the total energy is actually given by the kinetic energy plus mc squared. Okay, so the total energy is given by the gamma factor mc squared, and this here is equal to ke plus mc squared. The formula for the kinetic energy, just rearranging for it, is actually just equal to gamma minus 1 mc squared. In this equation, gamma is equal to 1 over 1 minus v squared over c squared. And this factor right over here is preventing us from reaching the speed of light. As you can see, if v is equal to c, this thing becomes 1, and then we're going to get 1 minus 1, which gives us a 0, and division by 0 is generally not good. So our new equation is going to be that gamma minus 1 mc squared, this here is my kinetic energy, is equal to v. I've actually filmed just this exact part as a standalone video before. Let's see if I remember how to solve this. So we can plug in 1 over the square root of 1 minus v squared over c squared, take away 1, mc squared is equal to E multiplied by capital V. So what we're looking for in this equation is the final speed v squared. Okay, that looks like it's going to be quite a lot of rearranging and algebra for 0.7 points, but let's have a go. So what I'm going to do is I'm going to say mc squared divided by the square root of 1 minus v squared over c squared. Take away mc squared is equal to EV. After a bit more rearranging, we can say that mc squared divided by 1 minus v squared over c squared is going to be equal to EV plus mc squared. Okay, I really want to isolate v, so I'm just going to flip this entire expression. So I'm going to go 1 minus v squared over c squared like this is going to be equal to 1 over ev plus mc squared. Now this should have been divided by mc squared, so I'm just going to write a factor of mc squared up here. Now let's square everything, and then we're going to get 1 minus v squared over c squared is going to be equal to m squared c to the power 4. Divide that by ev plus mc squared. All of this is squared. Okay, we're sort of getting there. Now I can bring the v squared up onto the other side, and what I'm going to get is that v squared over c squared is going to be equal to 1 minus m squared c to the power 4. Divide that by ev plus mc squared. All of this is squared, and v squared will be equal to c squared, and then 1 minus m squared c to the power 4 ev plus mc squared squared, kind of like this. We can just square root everything. So I'll tell you what, let's do that. And I'm gonna add a square root sign over here. I think that's right. Okay, question 2. So for particles with high energy and low mass, the relative deviation delta is equal to speed of light, take away the speed, divided by the speed of light of the final velocity is very small. Find the first order approximation for delta and then calculate it for electrons. Okay, so first of all, we're looking for a first order approximation, so we're probably going to have to involve either the Taylor series or the binomial expansion. So what are we actually trying to figure out? Okay, well, let's write down an expression for it. So for A2, we're looking for delta, which is equal to C take away V divided by C. Okay, this is equal to C over C, which is 1 minus V over C. Now, in the previous question, we had an expression for V, so let's substitute that in here and just see what happens. So our expression was c and then the square root of 1 minus m squared c to the power 4, and this is divided by ev plus mc squared, and this whole expression here was squared, and this is divided by c. Okay, as we can see, these are going to cancel out. And now what are we left with? We're left with delta is equal to 1 minus root 1 minus m squared c to the power 4 ev plus mc squared squared. Okay, so we want a first order approximation of this. I imagine the question wants us to apply either the Taylor series, which are on the specification for the International Physics Olympiad, or an approximation, or the binomial expansion. But there's a formula actually, which is given in the British Physics Olympiad formula booklet, and I think I remember it. I'm going to write this over here, that 1 plus x raised to the power of n is approximately equal to 1 plus nx, if I remember correctly. Okay, so we're going to apply this to this expression over here. Okay, what are we going to get? We're going to get that delta will be equal to 1 take away. Now this square root is essentially equivalent to n is equal to a half. This should be equal to plus n, which is negative halves, like that, negative 1/2. And then multiply by x. Now our x is this, m squared c to the power 4 ev plus mc squared squared like this. Things are starting to cancel out now, which is typically a really good sign in physics problems. So this here, the 1 and the 1 are going to cancel out, and what we're going to be left with is just a half m squared c to the power 4. And then we have EV plus MC squared like this for delta. We're probably not done with approximating though. I'm sure if we calculate it in this formula, we're probably gonna get full marks. But just to make it even simpler and save a little bit of time, EV is going to be significantly greater than MC squared. Now, why is that? The energies of these electrons are of the order of giga-electron volts, tera-electron volts, and MC squared, mass of the electron multiplied by the speed of light squared, is going to be a much smaller number in comparison. Okay, so because of that, we can say that delta is going to be equal to a half m squared c to the power 4 over EV. I think that's correct. Well, let's see. Let's plug in some numbers. So this here will be equal to a half m squared, 9.11 times 10 to the power minus 31 kilograms squared, multiplied by the speed of light to the power 4, 3 times 10 to the power 8. Raised to power 4. We might be given some slightly more accurate values for these fundamental constants in the International Physics Olympiad booklet, but I'm just going to go from memory. Divided by E, which is 1.6 times 10 to the power of minus 19. Now, what was the voltage in this question? So 60 giga electron volts. So this here will, the voltage that they pass through is going to be 60 times 10 to the power of 9. Okay, let's see what that gives us. Wait, my answer was suspiciously small, and yeah, so initially I got around 3.5 times 10 to the power minus 19, and yeah, sure enough I realized that I've forgotten to carry through a square, so let's just amend this. Okay, that's a little bit better. I got around 3.647, so let's call it 3.65 and multiply that by 10 to the power of minus 11. And this quantity here should be unitless. Just another tip if you're taking Physics Olympiads, if you're typing in a whole bunch of constants, most calculators have the inbuilt constants, so make sure that you know how to work with them really quickly. I couldn't remember, so I ended up just typing these manually, which is quite time consuming. So next question, this one is about an entire point, so it's probably going to be quite hard. Well, let's see. Derive an expression for the uniform magnetic flux density B necessary to keep the proton beam on a circular track. The expression should only contain the energy of the protons E, the circumference L, fundamental constants, and numbers. You can use suitable approximations. Once again, perfect. I do love using approximations. And we want to calculate the magnetic flux density for a proton this time. Okay, there's a couple of equations that we can use. So for a proton that is orbiting at a constant velocity, and if we apply a constant force to it, and the velocity is not a function of time, we normally would use the fact that mass times acceleration, which for circular motion turns to mv squared over r, is equal to qv cross b. However, in this case, the direction of the field and the velocity are going to be perpendicular, so this thing just turns into mv squared over r is equal to qvb. Obviously, there's a big problem with this equation. So the relativistic momentum has a gamma factor attached to it. Now, since F is equal to dp by dt, if the velocity is constant, we can just actually add in our gamma factor in here. If the magnitude of the velocity is a function of time, this turns into a really interesting problem. I think I remember actually, but in general, if the velocity is a function of time, we get that the force was gamma cubed A, I think, or something like that. This was actually a problem in the Asian Physics Olympiad, and it was a really cool derivation, so it might be worth having a browse. Let's get rid of one of these velocities, and we just get that gamma mv over r is equal to qb, meaning that B will be equal to gamma mv divided by Q. It's the protons we're talking about, so Q is just equal to the elementary charge. So this here will be R times E. But in this problem, we want to derive it in terms of the energy. Okay, well, the total energy, E, is equal to gamma gamma mc squared. So this means that gamma will just be equal to E over mc squared, where m in this case is the mass of the protons. Okay, so let's plug that in here. What do we get? We get that B is equal to gamma, which is going to be E mv, and then we have a factor of mc squared, and then an r and an e. Okay, cool. Now we can use suitable approximations. So, well, in the previous question, we found out that for particles which are traveling around the Large Hadron Collider, their relative difference to the speed of light is tiny. So let's just assume that v is approximately equal to not v. Let's assume that v is approximately equal to c. Okay, what is that going to give me? And that's going to give me that b is equal to e m. The m's are going to cancel as well. How did we not spot that? So then this here will be a c, and then divide that by c squared re. Okay, this here will then give me e over c re. Now, we want to get rid of the radius. We know that the circumference L is equal to 2 pi r, meaning that r will be equal to L over 2 pi. Okay, well, b will then be equal to e over c. Rather than r, I'm going to write L and then 2 pi. This looks suspiciously simple. Let's do a couple of sanity checks. The greater the energy, the more magnetic flux density is actually required. That makes sense. We've got a factor of 2 pi. These factors of pi just always sneak into the geometry of physics problems. We've got L. The larger the circumference of the ring, the less magnetic flux density is required. Okay. Tell you what, let's calculate this for a proton. So the expression was that B is equal to E2 pi over LEC. Okay, now what was the energy of the proton that they want us to figure it out for? It's 7 tera electron volts. So that would be 7.00 multiplied this by tera, which is 10 to the 12, multiplied by the elementary charge E, and then multiply this by 2 pi. Now, the elementary charge will end up cancelling in a second. Actually, we know the circumference L. What was L? It's given to quite a lot of significant figures in the question. So 2, 6, 6, 5, 9. I'm probably not gonna give my answer to this many significant figures, but let's just roll with it. E, which is gonna cancel out. Boom, be gone. E, and then multiply this by the speed of light, 3.0 times 10 to the power of 8. Okay, now let's see this. This here is going to give me around 5.49 Teslas, which into my significance, I think I've used a little bit lower than what the question provides, should be 5.5 Teslas. Now this answer, I think, kind of makes sense. Now it's not part of the question, but it's absolutely fascinating to compare this to the classical results. This question actually tells us why Einstein's theory of relativity is actually correct. Tell you what, let's even step outside of the question and let's calculate the classical result purely for fun. Okay, so this is not actually part of the question, but it's going to be so much fun to actually calculate. So we can say that classically, if I can spell it, we can say that mv squared over r is going to be equal to EV. This here is going to be cancelling out, meaning that B should be equal to mv over RE. The classical energy is going to be equal to mv, a half mv squared, meaning that the speed v is going to be equal to 2ev divided by the mass square rooted. Okay, so we can plug this into here, and we're going to get that B is going to be equal to m root 2ev divided by the mass divided by r times E. Okay, let's plug in some numbers. And we get a much smaller result. I got around 0.09 Tesla. Now, with special relativity, well, in the actual world, when you try to accelerate particles close to the speed of light, we keep pumping in energy and their momentum increases, but you know, their actual energy just barely increases. So in order to keep them on their track, we need to apply a monumentally higher force. Unless I've made a mistake somewhere here when plugging in the numbers, do let me know if I have. Okay, so it was a lot of fun, but not part of the question. So let's see what the rest of the question actually has for us. Okay, radiated power, and yes, we've got dimensional analysis. Now, I really enjoy dimensional analysis problems. However, I'm perfectly aware that they are problems where you are just generally quite likely to do a mistake because they often involve a system of equations. Okay, so what do we know? An accelerated charged particle radiates energy in the form of EM waves. The radiated power of a charged particle that circulates with a constant angular speed depends only on its acceleration A, its charge, the speed of light C, and the permittivity of free space. Use a dimensional analysis to find expression for the power. Okay, so we're going to say that power is some function of the acceleration A to the alpha, its charge Q to the power of beta, the speed of light C to the power of gamma, and the permittivity of free space epsilon naught. So that's going to be raised to the power of, I've got alpha, beta, and gamma. These are typically used for dimensional analysis. I think I've run out of letters, or my brain has just gone blank in thinking of a letter. I am just gonna choose X. Why not? It's a very good choice typically for an unknown. Okay, we're just gonna roll with it. And let's think about what the units are going to be. So in terms of units, power is joules per second. So the unit of power, so 1 joule is equal to kilograms meter squared s to a power of -2. This can easily be derived from, for instance, a half mv squared or mc squared, mass times speed squared. So this means that power, which is joules per second, is gonna end up having units of kilograms meters squared s to the power of -2 divided by another set of seconds, i.e. s to the power of -3. Okay, so this here will then give me acceleration, which is meters per second squared raised to the power of alpha. Then charge, so Q is equal to IT, so this here will be amps seconds raised to the power of beta. And let's make a little bit of space here because we are going to end up needing it. C is the speed of light, so this here will be meters per second raised to the power of gamma. Now, what about epsilon naught? This one is not as simple. Tell you what, I'm just going to use Coulomb's law, which is F is equal to QQ over 4 pi epsilon naught R squared. Epsilon naught is equal to QQ over 4 pi. Let's get rid of the 4 pi actually, because it has no units. So over F R squared. So the units of E naught are going to be the units of charge squared. So it'll be A squared S squared divided by force, which is kilograms, meters squared, S to the power of minus 2. Oops, that's just meters rather than meter squared. But here we've got a factor of meter squared from R squared. Okay, let's simplify this a little bit. So this will be A squared, and then kg to the minus 1, meters to the power of minus 3, then S to the power of 4. Okay, that seems a little bit complicated, but quick double check. No, it seems right. Okay. So E naught is going to give me this, which is A squared kg to the power of minus 1, m to the power of minus 3, s to the power of 4 raised to the power of x. Let's get rid of this because we're going to need that space to solve our system of linear equations in a minute. Okay, what are we going to get? That kilograms, meter squared, s to the power of minus 3 are going to be equal to, okay, m to the power of alpha, s to the power of minus 2 alpha, a to the power of beta, s to the power of beta, m to the power of gamma, s to the power of minus gamma, and then a to the power of 2x, kilograms to the power of minus x, m to the power of minus 3x, s to the power of 4x. Now let's group terms together. So this here will give me, let's take care of the masses first. That will be m to the power of alpha plus gamma minus 3x. Let's take care of the seconds. So it'll be minus 2 alpha plus beta. That's this term, and then minus gamma plus 4x. And that's taking care of those terms as well. And what else have we got? We've got the amps, which are beta plus 2x, like that. The only thing left is the kilogram, which is to a power of minus x. Okay, so this has to be equal to kilograms to the power of 1, meters squared, s to the power of minus 3. Now I can immediately spot that there's an easy one, which is this one. So kilogram to the minus x has to equal to kilograms to the 1, meaning that minus x has to be 1, meaning that x has to be equal to minus 1. Beta plus 2x, what is that for? That's for the amps, is going to be equal to 0 because there's no amps on the other side of the equation, meaning that this power here has to add up to 0, giving us a factor of 1. So beta plus 2x is 0. So beta minus 2 is equal to 0. Beta is just equal to 2. Nice and easy so far. I hope it remains this way. We also have that alpha plus gamma minus 3x, and x is minus 1, so it's going to be plus 3. This here is for the meters, so this here is going to have to equal to 2. Okay, so that means that alpha plus gamma is going to have to give me -1. And I've got one more equation, minus 2 alpha plus beta minus gamma, and then plus 4x, this is for seconds, is going to have to be equal to -3. Now we know quite a few of these already, so we can say that minus 2 alpha plus beta, which we know, is equal to 2. And then minus gamma. Do we know gamma? Nope, we don't know gamma. Like that. -4, because x is -1, is going to be equal to -3. Okay, minus 2 alpha plus minus gamma. And then what do we have? 2 and -4 is going to give me a -2 is equal to -3. Minus 2 alpha minus gamma is equal to -3 plus 2, which is going to be equal to -1. Okay, so now we need to express gamma as a function of alpha or vice versa. So let's just say that gamma is equal to -1 minus alpha, which is going to give me -2 alpha minus gamma, which is +1 plus alpha is equal to -1. So what is that going to give me? -2 alpha plus alpha is going to give me minus alpha. Plus 1 is equal to -1 minus alpha is equal to -2. Alpha is equal to 2. If alpha is equal to 2, then gamma is going to be -1 minus alpha, which is why am I so slow with basic arithmetic? -1 minus 2, which is going to be -3. Finally, we have x is equal to -1, beta is equal to 2, alpha is equal to 2 as well, and gamma is equal to -3. Now, it's so probable to make a mistake on these. Even though they're quite easy, it's so easy just to forget a minus sign. And we can plug all of these values into our expression for the power. Let's make some space. And shall we just write this in a different color just to differentiate that here? But our power is going to be equal to a to the power of alpha, which is 2, q to the power of beta, so that's q squared. And then we have c to the gamma, which is -3, so speed of light. And then E naught, like this. And this here should be our final expression for the power. So for the next part, we are told the real formula for the radiated power contains a factor of 1/6 pi. Okay, so they're giving us a constant for this, I think. So let's add in a factor of 1/6 pi. And then a full relativistic derivation gives an additional factor of gamma to the power of 4. And it looks like might be complicated. Okay, calculate the power for a proton of energy 7 tera-electron volts. Note table 1. Okay, you may use suitable approximations. Okay, so tell you what, let's rewrite this formula and start onto the next page. I don't think this one is too bad because we know that the total energy in relativity is equal to gamma mc squared, and we're given this in tera-electron volts, so all we need to do is express gamma once again in terms of that, so gamma is just equal to E over mc squared. Okay, so this here will then give me the acceleration squared the charge, which is just the elementary charge, so Q is just equal to E. And then rather than gamma, I'm going to write E to the power of 4, and then I'm going to have a factor of mc squared raised to the power of 4. At the bottom, I'm going to have C cubed E naught. Okay, the acceleration How do we get the acceleration? I think given what we know in the question, we can do a cheeky classical approximation. So acceleration should be about equal to v squared over r. Now, this v is really close to the speed of light, so tell you what, let's just say that this is equal to c squared divided by r. Okay, so this means that the power is going to be equal to c to the power of 4 over r squared c to the power of 3 e squared e to the power of 4 epsilon naught mc squared raised to the power of 4. Now we can also get rid of r, because remember the circumference L is equal to 2 pi r, meaning that r is just going to be L over 2 pi. Okay, so to plug this into there, tell you what, let's just do this. We're going to get a factor of L squared. And then up here, we're going to have a factor of 4 pi squared. Talking about pi's, I've missed one of my factors of 6 pi here. I've only just noticed. Let's plug that into here. A bit of cancellations. Shall we simplify this expression a little bit? We can get rid of c to the power of cubed. This is going to be really tricky to put into a calculator. We should get around 7.867 or so. Multiply this by 10 to the power of minus 12 watts. Is this what the question is actually asking about? So going back to the question, let's have a look. Use dimensional analysis to find expression. We've done that. The radiated power of a charged particle. So this here is the radiated power of a single proton that's kind of moving along. But there's a lot of them, right? And that's why they've told us to note table 1. Okay, number of bunches per proton, 2808. And then we're gonna have number of protons per bunch is 1.15 times by 10 to the power of 11. This here should give me 2.2540 watts. And I have just made a mistake. Please note that in the Large Hadron Collider, there are 2 beams traveling in opposite directions. So the real answer should be this number multiplied by a factor of 2. Okay, A5, which is the final part of the first section. So at CERN, protons at rest are accelerated by a linear accelerator of length d is equal to 30 meters. So imagine that's the initial acceleration of the protons. 500 million volts, that's a lot of voltage. Assume that the electrical field is homogeneous. Hooray, we can use E is equal to V over D. A linear accelerator consists of 2 plates. Okay, well, that looks nice and simple enough. Positive plate, negative plate, electrons jumping through. We want to determine the time that the protons take to pass the electric field. So let's have a think. So A6. What do we actually know in this question? We know that there is an electric field that is applying a force. Now, we know that the force is equal to the electric field multiplied by the charge. This here will be equal to V over D, and the charge is just E. The force is equal to dp dt, the rate of change of momentum, which is equal to V over D, multiply this by E. Now, the momentum and its magnitude is a function of time. Pretty sure I remember the result from relativity. It's also appeared on the Asian Physics Olympiad in one of the questions which I filmed previously. but the gamma mv by dt is actually, if I remember correctly, gamma cubed ma. Okay, so let's see, can I use this result here somewhere? So I can go gamma 3 ma, acceleration, let's say that this here is my x-coordinate. To go from here is the acceleration is going to be the second derivative, like that, which is equal to v over dE. Okay, meaning that x dot is going to be v dE, like this, and then m over gamma cubed. Now x dot will be equal to VE over dm, 1 over the square root of 1 minus v squared over c squared, which is equal to VE 1 minus velocity is the first derivative, and it's a square. I don't like the look of this differential equation. I don't think this might be a good approach. Let me know in the comments if you can find a solution to this differential equation. I think I'm going to approach the problem in a more simplistic way, which is probably consistent with what we were doing in the problem. So let's go back to the basics. We know that the net force is equal to dp by dt, which is equal to the rate of change of momentum. So the total change of momentum, dp, then over dt, that's just equal to, what did we say it was? It was v over d multiplied by e, like that. Okay, so we can probably figure out the time over which this happens if we just say that the total change of momentum is something. Almost like a normal high school problem. Delta P over delta T is going to be equal to Vd over E. Now, they're accelerated from rest, I imagine. Let's just double check the question is actually saying this. Yes, they're accelerated from rest. So we can say that delta P is equal to P2 minus P1, and P1 is 0. So delta P is P2. That's the final momentum after acceleration. Okay, now relativistic momentum is gamma mv, like this. And all of this happens in a certain time frame, delta t. And this here will be equal to Vd over E. We've got an expression for the speed at which they reach, approximately, and we figure this out the very first part of the problem. We also know that gamma is equal to 1 over square root of 1 minus v squared over c squared. Okay, this expression is going to be not very nice. I'm just trying to think if there's a good way of simplifying this. I think it might just be brute forcing near the end of this part of the question. I'll tell you what, let's just start plugging in and see what we get. So for gamma, we are going to get square root of 1 minus v squared over c squared, like this. Now it's really important for our work to start being really neat at this point, because I'm expecting a gigantic expression. And then the speed v, which is going to be given by c root of 1 minus mc squared. All of this is squared. Actually, tell you what, let's just write this as m squared c to the power of 4. Divide that by mc squared plus ev. We actually did an approximation, didn't we, that ev was a lot bigger, so let's just write that as ev squared. Also, it's going to save a bit of space, even if our final answer is a little bit off at the end. Okay, ev squared like this. Then we have a factor of delta t here, which is equal to v over d, and then multiplied by the electron charge. I think I've got an equation with one unknown, don't I? Because I know the mass of an individual proton, I know the speed of light. Can I assume that v is approximately equal to c in this case? Well, no, I can't, because then my equation is going to break down. Let's just keep expanding and see what happens. We're going to have mc, and then 1 minus m squared c to the power of 4, divide that by EV for voltage squared. Okay, divide that by the square root of 1 minus v squared, which is going to be equal to c squared, and then square root of 1 minus m squared c to the power of 4. Divide that by EV squared, divide that by c squared. Okay, end of the square root, delta t. Okay, maybe we're getting somewhere. So this here will be equal to Vd times E. Okay, a bit of cancelling. This and that. Now, let's rearrange for delta t. So delta t is going to be equal to all of this. mc 1 minus m squared c to the power of 4 over ev squared. Divide that by, it's really important to take the final bits of the Olympiad almost in a way a little bit more slowly, because it's just so easy to make a mistake after you've been kind of doing a question for a while, and like a little rearranging mistake here and there that can cost you quite a lot of marks. If I do a mistake, it's obviously on purpose, so to show you what not to do, right? Then square root of 1 minus root 1 minus m squared c to the power of 4 over ev squared like this. This is getting complicated. And because we're rearranging for delta t, we've essentially kind of taken this from here to here. So to rearrange for it, we need to multiply this by the distance, divide by the voltage and the elementary charge. And we've got yet another monster of a substitution, unless there's a little bit of an easier way to substitute these. But at this stage, I'm just going to brute force them, and I'll probably just put them into Wolfram Alpha, and the result should just magically appear on the screen for you. So I got around somewhere around 1.8785, let's go 1.88 times 10 to the power of minus 7 seconds. This is actually not too far, because the mark scheme gives around 218 nanoseconds, which is pretty close. They're about the same, especially keeping in mind that a lot of the values I just kind of wrote from memory rather than using the official formula booklet. Okay guys, hopefully this video has been very useful and entertaining. This was the end of part A. Let me know if you would like me to have a go at part B in a different video. What you should do until then though is have a look at a really special video I did at Oxford University with Tom Rocks Maths, who gave me lots of tips and gave me a mathematics exam, and you will gain so much from this video. Have a look right over there.